If layer 1 was the HTTP receptionist, layer 2 is the phone book entry.
I like that analogy.
The fundamental problem that the Kubernetes service object solves is the ephemeral nature of pods. In a dynamic cloud-native environment, pods are cattle, not pets. They are scaled up, they crash, they get moved to different nodes.
And every time that happens, they get a new IP
A
address.
completely new, unpredictable IP address. And yet, everything inside the cluster, from the ingress controller to other microservices, needs a static, reliable way to address that functional group of pods.
And that's the service object.
Correct. The service object provides that stability. It assigns a stable network identity, the cluster IP, which never changes for the entire lifetime of that service. When the ingress controller forwards the request, it's not targeting a specific pod IP. It's targeting this stable cluster IP.
So it's the crucial mechanism for service discovery inside the cluster network.
It's the core of in-cluster service discovery, yes.
So how does this static, stable address connect to the actual constantly shifting set of pod IPs? And where does that link happen?
That is the core mechanism, and it's managed by the Kubernetes control plane. The service object, in its YAML, defines a spec.selector.
Which is just a label query.
It's just a set of labels.
Well.
For example, app.dataProcessor. The Kubernetes controller manager is constantly running this query against all the running pods in the cluster.
And the result of that query that gets stored somewhere else.
Exactly. Kubernetes populates these auxiliary objects called endpoints, or in newer versions more efficiently, endpoint slices.
Okay, what's the difference?
Endpoint slices are just a more scalable version of endpoints. With the original endpoints object, if you had a service with 10,000 pods, you had one giant endpoints object with 10,000 entries. Every time one pod was added or removed, you had to update that huge object, which caused a lot of churn in the control plane. Endpoint slices break it up. So you might have 100 endpoint slices, each with 100 pod IPs. Now, if one pod changes, you only have to update one small object. It's much more efficient.
But the function is the same. These objects contain the definitive, constantly updated list of live, healthy pod IPs and the ports they expose.
The ground truth: if 5 pods match the selector and are considered ready, the endpoint slice will list those 5 specific IP addresses. And this list of real destinations is what the layer 3 components, what we're about to talk about, the kube proxy, actually use for forwarding traffic.
It's important to clarify the different service types, too, because they dictate how that stable cluster IP is exposed.
Right. There are 3 primary types you'll encounter. The first is cluster IP. This is the default, and it's internal only.
So this is for when service A needs to talk to service B inside the cluster.
Exactly. It's stable, but it's completely unreachable from outside the cluster network fabric.
Okay, what's next?
The second type is node port. This one is a bit more direct. It exposes the service on a specific fixed port across every single node's physical IP address.
So if I have a 100-node cluster, I can hit port 300.0.0.0.7 on any of those 100 nodes and get to my service.
Correct. This is often used when you need a predictable port exposed on the host itself, but it kind of bypasses the sophisticated load balancing of layer 1 and is generally less common in large production systems. It can be a security concern, too.
And the third type is the one we already mentioned.
Right, load balancer. As we discussed, this integrates with the cloud provider to provision an external L4 load balancer that targets the nodes and routes traffic to the services pods.
Okay, let's get into the failure modes here. Unlike the really clear L7 errors like a 404 or a TLS error at layer 1, layer 2 failures feel different. They're often silent and lead to these really frustrating timeouts.
We call this the silent failure. And the biggest red flag, the number one thing to check, is when the service exists and the cluster IP is correctly targetable, but when you run kube install get endpoints, the list is empty.
The phone book entry exists, but the office building is empty. Nobody's home.
Nobody is home, and 99% of the time this is due to a simple label mismatch. The label defined in the service selector, say app data processor, doesn't exactly match the label set on the running pods. Maybe there was a typo.
Data processor instead of data processor.
I've spent hours on that exact typo. The controller manager sees 0 matches, so the endpoint slice is empty. Traffic hits the stable cluster IP, but there are no backend destinations, so the packet usually just gets dropped at layer 3 when the kernel attempts to forward it, and you get a timeout.
So a quick check at kubectl get endpoints OYAML, followed by comparing the selector field in the service manifest against the labels in the pod manifest, is the essential debugging step here.
It's step 1 for any connection timed out error inside the cluster.
What's the second major failure at this layer?
The second one is the stale endpoint. This happens if a pod suddenly crashes, maybe it gets killed out of memory, but the control plane hasn't yet removed its IP from the endpoint slice.
There's a delay.
There's a slight reconciliation delay. So for a brief window, traffic continues to be sent to that dead IP. This is what causes those maddening intermittent connection drops, or 503 errors. One request works, the next one fails, the next one works again.
Because it depends on which endpoint the load balancer happens to pick.
Exactly. This really highlights the distributed state problem, doesn't it? The service definition is stable and logical, but the endpoint list reflects the dynamic, volatile reality of the cluster. That list is the bridge between the logical network of layer 2 and the physical forwarding system of layer 3.